Greetings, wonderful physics students. Captain Rod here, and I'm making this video to help you out with the first couple problems on your Unit 2 homework. So let's take a look. See, capacitance and electrical potential energy. So number one, a uniform electric field of 100 Newton per Coulomb points in the plus J direction. The coordinates are shown in centimeters. Draw potentials through each point. So, for starters, let's talk about that 100 Newton per Coulomb. That's an absurdly weak field. The electric fields can be much stronger than that. I'm just making up a value here for the purposes of providing you an example. So draw equipotentials through each of these points shown. Now keep in mind some things about electric potentials. Electric potential always decreases with the field, increases against the field, and it's constant when you make a right angle to the field. So here we have this electric field. If I move from here to here, right, that would be no change in potential because it's not moving with the field. So that should give you a pretty good example of what those equipotentials look like. Now, hopefully you watched my video here. I'll pull up the previous problem I made for you. Here's a video I made doing very similar stuff. So just refer back to that if you are having trouble with this, with drawing those potentials. Okay. I don't want to give away what they look like, but you should be able to draw potentials through those points pretty easily. All right, next, calculate a value of each potential, assuming that the potential at 0, -2 is 0. So this is just setting a datum. So one of those potentials has defined to be a potential of 0. And when you calculate the potential difference, right, potential difference is field strength times distance. And I'll just say magnitude of potential difference is field strength times distance. This is a uniform potential difference, or I'm sorry, this example has a uniform electric field, so this is as much math as you need to do this. Just keep in mind that the distances have to be in the direction of the electric field, or in the opposite direction. So part C. Oh, now by the way, this says to calculate a value, okay, and it's assuming this. So now part C. Let's see, what is the difference in potential between these 2 points? So you have a potential, you should have a value for this point and a value for this point, and it's the difference between them. And I'd like to add, just make sure you write down which one is at the higher or lower potential in some way, shape, or form. I don't want this auto-save on. All right, now, let's see. How much work must be done to move a proton from 0, 2 to -4, -1? So 0, 2 is here. I'll put my proton there, call that position 1. -4, -1 is here. Call that position 2. And what you want to do now is just write out the work energy theorem for this. And there'll be a work term. Now, the reason there would have to be a work term, see this proton here at position 1, if you let it go from rest, it's going to accelerate this way, right, because of this electric field. If you want to move it upstream of the field, if you will, you're going to have to apply some sort of external force. So there's going to have to be some external force applied to that proton to move it over to here. Now, where is that force coming from? Not important for the question. Just suffice to say there has to be one. And then when you write out the work energy theorem, the PE1 plus KE1 plus work equals PE2 plus KE2, there's a work term. And nobody said anything about changes in speed. So we'll just assume the kinetic energies at 1 and 2 are the same, subtract them off. And that should be enough to get you through that question. What is the change in potential energy of the proton? So remember how electric potential is defined. It is defined as potential energy per unit charge. So a slight rearrangement of this says that potential energy is equal to charge times potential. So take the charge of a proton and the value of your potential at these locations, and then calculate the change. And by the way, then compare it to the work term here, and something hopefully will be kind of evident. Question 2. Basically, it's the same question. All I've done is change the electric field direction. So what that's going to do is it's going to change the direction of your potentials. Right? And then keep in mind the potential at 2, let's see, 0, -2 is 0. So that's right, the potential right there. And then there's an equipotential that goes through there. That entire equipotential is defined to have a value of 0. And then answer all the questions forthcoming. So I hope that gets you through that problem, both of these anyway. Have a great day.